Hi guys, today I'm going to be talking to you about the impact of sampling frequency and signal gain on the accuracy of data when digitalizing physiologic stimuli. The main objectives include understanding why we digitalize physiologic signals, types of digitalized signals, and finally to understand sampling frequency and signal gain in signal processing. Now, the reason why we digitalize physiologic signals is because they give us a visual representation of our physiologic states, and we can make interpretation of these patterns visually, therefore making more accurate diagnosis. It is also efficient, provides real-time analysis, and accessible at any given time. Now let's take a look at some examples of digital signals such as ECG, EMG, airflow, and action potentials. Now let's take a look at ECG in a little bit more detail. If we're studying a patient's ECG, we can make interpretation of these patterns visually, and any abnormalities in the heart will display distinctive patterns. For example, a wider than average QRS interval may indicate a slower conduction of action potential down the bundle of His, and this may be an indication of Wolff-Parkinson-White syndrome. So what I'm trying to get across is visually recognizing abnormal patterns in these digital signals is much easier than other diagnoses. However, now the question we have to think about is, how do we know that these digital signals are a good representation of our physiologic signals? What do we have to check when we're measuring and collecting these samples? So there are two things that we need to consider when collecting these samples. First being signal gain or amplification, second being sampling frequency. And I'll go over why each is important when it comes to the accuracy of our data. Now, when we're measuring signals from our body, sometimes the electric signals are just too weak to be displayed or to have a clear visual representation on our computers. And this is where signal gain comes into play, where we increase the amplitude of the signal so that it is easier to interpret. This is kind of similar to the step in PCR, where we amplify small DNA fragments simply because they're too small. Now, sometimes signals can contaminate with noises because the process involves several stages of electronic circuits. Most importantly, though, potential delayed recovery occurs when we get an extreme large signal at higher gains. The signal amplitudes exceed the power supply voltage of the amplifier, and what happens is that the top of the signal gets flattened out. When this occurs, they can take several milliseconds to recover, delaying the time to reproduce signals. And this can be problematic when we're looking at interval-based diagnosis, such as QRS intervals in the ECG that we just talked about. This is why we need to find a range for signal gains that are not too low to be visually interpreted and not too high to cause delay recovery. Now, clipping is a method that we can use to eliminate delay recovery. Clipping is basically constraining on the range of data it can measure. So it basically cuts off a signal above a predetermined amplitude, which gives you a more accurate representation of our physiologic signals without delay recovery. It also eliminates any noise signals outside of this clipping plane. Now let's talk about how sampling frequency can affect the digital representation of our physiologic signals. Sampling frequency, by definition, is how often do we take samples of our signal. And this is important because if we're taking measurements of our signal at an insufficient frequency, then we will get an inaccurate representation, also known as aliasing. On the other hand, if we take excess samples at a more than enough frequency, we might get some noise and it might be heavy on our computer processing. Therefore, we also need a sampling frequency not too low to have inaccurate representation and not too high to acquire these noise signals and being heavy on our computer processing. Now, the Nyquist limit theorem tells us the perfect sampling frequency of signals, that we should take at least 2 samples for every cycle of the wave. If we take a look at the signal in the middle with 3 cycles, we're taking 6 samples, and the results closely resemble our original signal. And any sampling frequency less than 2 per every cycle, such as the one on the top and the one at the bottom, both results in inaccurate representation. This is known as aliasing, and just notice how it impacts the amplitude and the frequency of the original data. Now, the last slide, I'm just showing a table which compares the signal frequency of some physiologic stimuli and its appropriate sampling frequency, which is all above the Nyquist limit of 2x. And that will be it for my presentation. Thank you guys so much for listening.